In this video, we will be calculating the pH of a weak base, and it's exactly like calculating the pH of a weak acid, except we are going to use a Kb value, and our equation looks just a little different. So when a base dissolves in water, we represent the process with this generic equation here. So we have our base with water in liquid form in equilibrium with the base plus the addition of that proton, and then we have the OH negative also in solution, and that's our hydroxide. We leave the liquid out of the equilibrium constant expression, and then we get this as our Kb. So here is an example problem. Calculate the pH of a 0.100 molar solution of NH3. This is ammonia, which is a pretty typical weak base, a pretty common weak base. So I'm going to start out by writing the reaction between that ammonia and water, so NH3 in aqueous solution with H2O as a liquid in equilibrium with the NH4 plus ion in in aqueous solution. That's the ammonium ion, and OH negative, which is our really truly what we will be measuring for our base measurements. The Kb of NH3 is 1.76 times 10 to the negative fifth. Now I'm going to write out my equilibrium constant expression. So I have the NH4 plus, the concentration of the NH4 plus, multiplied by the hydroxide concentration all over the NH3 concentration. Now I'll fill in my ice chart. So I have the NH3 in equilibrium with the NH4 plus and the OH minus. I'm going to leave water out of this because it doesn't do anything. And then I have my initial concentration of NH3, which is 0.100 moles per liter, 0 for my ammonium, and then about 0 for my hydroxide concentration. There is a little bit of hydroxide in this solution to begin with because there is hydroxide in water, but we're going to forget about that because it's so negligible. Then I will put in my x's for the change values using the coefficients from the chemical equation, and then find the sum of each column to get my equilibrium concentrations. Now I'm going to rewrite my Kb, so I have 1.76 times 10 to the negative fifth, and I'm going to substitute in the values of my equilibrium concentrations. So I get x squared over 0.100 minus x. Now, because that Kb is so small, we can assume that this reaction happens very minimally. So it does not proceed to the right very much. It's a very left-sided or reactant-sided reaction. And because of that, I can eliminate the x from my subtraction equation. So I'm going to rewrite that without the x there, because if you subtract something very small, then it's almost like you didn't subtract anything because this is such a small x. So rewriting this, I get 1.76 times 10 to the negative fifth equals x squared over 0.100. I'm going to cross multiply here with my calculator. So 0.1 times 1.76 times 10 to the negative fifth is 1.76 times 10 to the negative sixth. So x squared is equal to 1.76 times 10 to the negative sixth. Now I'm going to find the square root of both sides. So the square root of x squared is x, and the square root of 1.76 times 10 to the negative sixth is 1.33 times 10 to the negative third. So I get 1.33 times 10 to the negative third, and that is in moles per liter. That is my x, and it just so happens that that is the concentration of my hydroxide as well. So the hydroxide concentration is 1.33 times 10 to the negative third moles per liter, and I'm going to use this to find my pOH. So the pOH is equal to the negative log of the hydroxide concentration. So I'll substitute in there my 1.33 times 10 to the negative third. And on my calculator, find the pOH. So the negative log of this, of my previous answer, is 2.88. So the pOH of this solution is 2.88, but the question is asking me, or the problem is asking me, to calculate the pH. And remember, pH plus pOH equals 14. which means that the pH is going to equal 14 minus this pOH, which equals 11.1. So the pH of this solution is 11.1. Now, does that make sense? We have a basic solution. It's a weak base. It's not the full dissociated base. So the pH is less than what we would expect it to be in comparison with a strong base.